Okay, so we begin with the second part of our chapter, which will now talk about pressure, right? We have done with force. Now let us understand about pressure. So, a couple of you who have done this topic already in your classes, you will be reading that pressure is the unit of pressure is the measurement given by force upon area. So we will be dealing pressure at a very simple stage out here, and the importance of pressure to understand here is that if your concept becomes right here, it becomes easy for you to understand pressure when you'll be dealing with same concept in say grade 11 and partially in grade 9. So the topic deals with pressure in solids, pressure in liquids, and pressure in gases. So we start our discussion with pressure in solids. So in order to understand pressure exerted on solids, what I'm trying to do is that I'm trying to conceptualize a cuboid, right? So I hope you all are familiar with the shape of a cuboid. What's a cuboid? It's just like a shoebox that you have at home. So let's also get ourselves exposed to a little bit more mature drawing of a cuboid in terms of understanding the three dimensions of a cuboid. So the very easy format of drawing cuboid, just make two rectangles, join the edges. What I'm doing now is that I'm extending each of the dimension, that is the length, the width, as well as the height, and trying to show them as a part of the three dimensions, one being x, one being the y-axis, and one being the z-axis, right? So this is a cuboid, which is a three-dimensional figure, and this three-dimensional figure or a solid object has now been drawn in front of you, showing you the aspects of all the three dimensions, with length being on the x-axis, the height being shown on the y-axis, and the width being shown on the z-axis. We are measuring the length, say, in terms of L. We'll measure the width in terms of either a W or a B. Width is also known as breadth, as you might have learned till now. And the height has been shown as H, which stands for the height. Right. Our objective is to understand the concept of pressure, and in order for pressure to exist, there has to be a force. So what we'll now understand is how does a force act on this particular object, rather to be more precise, on a face of this particular object. How should the force act so that it qualifies for contributing to pressure, right? So far in books, if you have seen, you will see that pressure is defined as force upon area. Now, that is how we always, mug up our definitions. But let us try to understand, is any force going to contribute to pressure? Or are there any specific type of force that is going to contribute to pressure, right? So let's see. Now, let us imagine that there is a force which is acting upon the top surface of this cuboid, and before that I've just drawn an axis. It's pretty difficult to give a voiceover, the reason is because you need to match your voice along with the video that has happened. I don't remember every frame of how the class was conducted. So this is the axis. So the blue line shows the axis, which is like the center line of the top surface. And remember, the top surface of this cuboid is like a rectangle. Obviously, if you see the top surface of a shoebox, it's like a rectangle. Now, say suppose a force is acting on it, and this I have indicated with this yellow arrow. There's a force which is acting on this top surface. Now, at present, if you start, talking about pressure, maybe to the very little that you have learned or you must have read, you will straight away compute pressure, saying that pressure is given by the force that is acting on it upon the area. So, which area? The area of the surface. Okay. So, let's understand. Bear with me because, okay, so this force is not acting exactly perpendicularly. The force is acting at some angle x, and I say x is acute. I know I presume that you know what is acute. Acute is an angle that is more than 0 degree and less than 90 degrees. So I have a force, and this force is creating an acute angle. Now, the first question that comes, will this force contribute to pressure? I mean, let me put my words in a better sense, that when I say pressure is equal, force equal to, sorry, pressure equal to force upon area, this force is not the force that we will be considering, right? The force that we consider for pressure computation is the force that acts at 90 degree to a surface. Now look at the second yellow line or the yellow arrow that I have drawn, and that is a force F. This force is acting at 90 degree. It's a special force, and we call this force as thrust. So what is thrust? Thrust is the force that acts perpendicular to a surface, and while computing pressure, the force that we consider is always the thrust. Like we say, the thrust of an aeroplane. The thrust gives the aeroplane a vertical lift. Now, you might also ask, sir, does F dash not contribute to pressure? Yes, F dash will also contribute to pressure. However, at this stage of your curriculum, you will not understand how F dash contributes to pressure. There are some components of force which are some higher level physics. So at grade 8 level, if in a diagram they show a force that is contributing to pressure, they will always show the force acting perpendicular to the surface. Okay, so what is thrust? Thrust is a force that acts perpendicular to a surface and it acts at 90 degree, and it is the thrust which is going to be responsible for the computation of pressure that acts on the surface. Which surface? The top surface. Children, a cuboid has got 6 surfaces. Right now we are only trying to compute what is the pressure that is exerted on the top surface. So in order to compute that, we need a force and we need the surface area. So the force should be acting perpendicular to the surface, and the surface area should be the area of the face on which the force is acting, right? So it's just not any other force, it's the perpendicular force. So I now define my pressure. Pressure is defined as force upon the surface area, and which to be very precise, what type of force? Well, the force that acts perpendicular. So I would write this as the force is my thrust, and this is being divided by the surface area. Now, when you talk about the surface area, try to imagine the top surface of a cuboid or a shoebox is nothing but a rectangle. So it would be the area of that rectangle which is actually your top surface, right? So let's quickly have a summary. What is pressure? Pressure is defined as the force, or rather the perpendicular force called thrust, acting on a area. So pressure is force upon the area. So we will now quantify it, get its SI unit before proceeding further. So as we draw this diagram, we should also understand that is every force a thrust? No, every force is not a thrust. However, every thrust is a force. So force, that is the thrust, divided by the surface area. And children, tell me now, what should be the surface area of this top surface? Well, the top surface area would be a rectangle whose length is L and the width is how much? The width is W, right? Because we are worried about the top surface. We are worried about the top surface. So the length will be L and the width will be W. I know you would say that no, sir, it is looking like a parallelogram. It is not a rectangle, but this is a three-dimensional drawing. So it's actually a rectangle. Okay. And a cuboid has got how many faces? A cuboid has got 6 faces. You got two similar rectangles on the top and bottom. You got two similar rectangles on the front and rear. And you got two similar rectangles on the right and left. So computing the area for this surface would be the length L multiplied by the width W. Now, what I'm trying to show here is with those lines is that I am worried about the surface area of only the top surface, and the top surface resembles the shape of a rectangle, and we know that the area of a rectangle is length times the breadth. In this particular top surface, the length is L, whereas the width is how much? The width is W. So it is F divided by L times W. Now we need to also specify what is the unit for pressure. Our next target should be unit for pressure. So we understood pressure is force upon area. The force should be the thrust. So area, obviously the area of the surface. Force is specified in Newton, and unit for area. Now look at the area. We have got a length and we have got a width. Both are in SI unit expressed as meters. So it will be meter times meter. If you have done a little bit of exponents, then meter times meter is meter square. So this is Newton upon meter square. So what is the unit of force? Oh, sorry, pressure. The unit of pressure is Newton upon meter square. And for this, we have given a special name, which we call as Pascal, right? 1 Newton upon 1 meter square is called a Pascal. So 1 Pascal is 1 Newton upon 1 meter square. Now, children, when we come across units, these are called derived units of any quantity, we are also expected to define the unit. So how do you define a Pascal? A Pascal can be defined as the pressure. 1 Pascal is the pressure exerted on a surface when a force of 1 Newton acts perpendicularly on a surface area of 1 meter square. Some books will use the word normally instead of perpendicular. Both mean the same. In physics, if I say this force acts perpendicular, it means the same as this force acts normally. So what is 1 Pascal? 1 Pascal is said to be the force, 1 Pascal is said to be the pressure exerted on a surface when a force of 1 Newton acts perpendicularly or normally on a surface area of 1 meter square. Right. So we'll write the definition also. 1 मीटर स्क्वायर के एरिया के ऊपर अगर 1 न्यूटन फोर्स परपेंडिकुलरली उसके ऊपर एक्ट करे, तब उस सरफेस पे जो प्रेशर पैदा होता है वो 1 पास्कल होता है. राइट. So I was saying the other day, if your cheek is 1 meter by 1 meter, say you are a square cheek which is 1 meter by 1 meter, and a force of 1 Newton comes perpendicularly on your cheek, then the pressure exerted on your cheek is 1 Pascal. There we go with the definition now. 1 Pascal. 1 Pascal is the pressure exerted when a force of 1 Newton acts perpendicularly or normally on a surface area of 1 meter square. Sometimes, children, we also should, have a guess or a vague measurement of how much does each value correspond to. So when we talk about 1 meter square, what is 1 meter square? You must have gone to these clothes stores and suitings and shirting stores like Ramon's and all, and there you will see a person taking out an iron stick, and then with that he will measure the piece of cloth and cut it and give it across to you. So that stick is 1 meter. Now imagine a square which is having its side equal to that stick. Now that square's area will be 1 meter square. In fact, the table which is there right in front, that's approximately 1 meter. So if the width of the table would have been a 1 meter, so it's 1 meter square. On that, if a force of 1 Newton acts perpendicular, then the pressure is said to be 1 Pascal. All right, so take your time and nicely draw this diagram. I hope you have understood what we tried to study. We tried to study pressure exerted on solids. So in order to understand pressure exerted on solid, we should first understand who all contributes to this pressure. So definitely force contributes to pressure, and that too the force should act normally or perpendicularly on the solid, and we are interested on the surface area on which the force is acting. Now you have got 6 surfaces out here. In this diagram initially we just considered what about pressure when the force acts on the top surface. We will now try to also have other iterations. Look, now I am trying to show a force which is acting on the right hand side. Okay, on the right hand side. Let's say this force is given by F2. F2 is a force which is acting at 90 degree to the right hand side. So how much will be the pressure? You should first ask, is F2 acting perpendicularly? Yes, F2 is acting perpendicularly. So the pressure exerted by F2 would be equal to the value of F2 divided by the area of the right side face. And what is the area of the right side face? The right side face is also like a rectangle whose length can be related to the width, and the height is the height of our current cuboidal block. So its area would be W times H, right? Its area will be W times H. Try imagine a shoebox and the right side of the shoebox. So right side of the shoebox is also a rectangle and its area will be W times H. So that's also meter into meter, meter square. So this is the pressure exerted on the right side. Let's now try to have another force, say F3, which is acting perpendicular to the front surface, So how do you compute pressure for this? Pressure is again force upon area. Please ask yourself the question, is F3 acting perpendicularly? Yes, F3 is acting perpendicularly. So our pressure would be given by F3 divided by the area of the front surface, and the front surface resembles that of a rectangle, and its area will be given by length times the height. Length times the height. Okay. So don't think that the pressure exerted on all surfaces are the same, because they will depend upon what is the force that is acting on any surface, and it will also depend upon what is the surface area of that surface on which the pressure is acting. So for this surface is given by F3 divided by length times W. I hope now you have understood. The only thing you need to take care when such concepts about a cuboid is given, that every face of the cuboid has a different area. Every face is a rectangle. Try to visualize the rectangle. Try to visualize what is contributing to the length, what is contributing to the width. The product of both will be the surface area. Right? So this is the broad concept of pressure. So don't just get carried away that pressure is force upon area. Yes, it is force upon area, but the force is a special force which acts perpendicularly. Don't be under the assumption that if the force acts at an angle, it doesn't contribute to pressure. It does contribute to pressure, but the computation of pressure for such a case is beyond your level right now. Right? So at our level, we will be only considering for pressure contributed by force that are acting perpendicular on a surface, and such force are called thrust. And when anything acts perpendicularly in geometry or in physics, we also use the word normally. Pressure acting normally and pressure acting perpendicularly all means the same. Okay. Whether I explained to you about what is a meter stick, I don't remember. Yeah. So what is 1 meter square? 1 meter square is a square whose edge is equivalent to 1 meter. And how to understand 1 meter is the size of that stick, the iron stick, which a garment store or a cloth store person uses to measure the length of the cloth before he cuts it out and sells your measured piece to you. So that's called 1 meter. Roughly, as I was saying, our table is around 1 meter on the length. If the width would have been in a meter, then it would be 1 meter upon 1 meter, which is the area of a square with edge 1 meter, right? So hope no doubt is there on this first part of the explanation of pressure. What we will now do is that since we have understood what is pressure, we'll understand some daily aspects, and we will see some daily happenings and things that happen around us, and we'll try to, uh, put the concept of pressure and see how the things have been designed so that the pressure exerted is taken care of. Always remember the six, whenever it's a cuboid, it contributes with six surfaces. So now that we have understood, let's see some cases where we will see what happens on the variation of force and area. So in order to understand that, let us take some example from our ongoing mathematics chapter, that is rational number. Okay, say I have a fraction 3 upon 5 and I have another fraction which is 3 upon 7, and I ask you which one is bigger, which one is bigger, right? You did not do anything. You just use the same concept as I told you. Three mangoes eaten by five guys and three mangoes being eaten by seven guys. So where will you see a happy face? The happy face will always be when three mangoes are eaten by five guys, right? So whenever it's a numerator and a denominator, if the denominator value goes up, then you will find that the quotient's value comes down. That's the reason when we had a 3 by 7, we won't have happy faces out there. And if the denominator's value goes up, the quotient's value comes down. And as the denominator's value comes down, the quotient value increases. So if we look at pressure, pressure is the quotient where the numerator is force and the denominator is area. So if you increase the area, obviously the pressure will come down. During such type of an iteration, children, remember, you don't have the right to touch force. Force is always kept as constant, right? Force is the numerator. If you see our rational number example also, it was three mangoes on both the cases. However, on one side we had five children eating them, and in one case we had seven children eating them. So force upon area is a numerator upon denominator whose quotient is given by pressure. So if the area fluctuates, the pressure varies oppositely. So if the area increases, the pressure falls down. And if the area decreases, the pressure builds up. Remember, during this iteration, we are not allowed to change the force. That's what I'm trying to show you. Now, in my second assessment, what we are trying to do, we are keeping the denominator constant and we are trying to increase the numerator. That is three mangoes eaten by five children, four mangoes eaten by five children. Obviously, four mangoes eaten by five children, we will get more as a quotient. That means in any fraction, if the denominator is kept constant and if the numerator is increased, the quotient value increases. And if the numerator is decreased, the quotient value decreases. So if I now play on force, right, and I try to vary force and I keep the area as constant, I will find that the pressure varies directly with that of what you call force. If the force increases, the pressure will also increase. But let us first understand examples in which we will keep the force constant and we will only vary the area. And what is in our mind? As area decreases, pressure increases. I hope you have understood this through the illustration of the fractions that I have given, right? So let's now see pressure as force upon area. This time what we will do, we are going to keep area constant. We're keeping area constant, that is we have frozen the denominator, and what we will do, we will vary the numerator. So if the force goes up, the pressure goes up, and if the force comes down, the pressure also comes down. As simple as that. Remember, with denominator it's a inverse, with a numerator it's always direct. Now let's understand some examples where the force will be kept constant and we will vary the area. So let's say we are in a garden, there's a gardener out there, and the gardener is interested to water his plants. So all he has is, he has a water hose in his hand, and the water hose is actually connected to a tap. So, and the tap has been opened, fully opened. Fully open means, what we try to say here is that the maximum force that the water can exert, he is utilizing it. Okay. The maximum force that a water can exert, he is utilizing it. So I have a tap and the tap is fully open. That means I have frozen the numerator, fully open. But the issue is that despite the tap being fully open, and which means that the water is coming with its maximum force, the water that is gushing out of the pipe doesn't is unable to reach the plant. He's unable to water the plants. Okay, he has fully opened the tap. He can't expect more flow of water, or he can't expect more force, but poor fellow is unable to water the plant. So what he does, look at the opening of the pipe, which we call as orifice. Okay, so the opening of the pipe, I'm drawing, it must be circular. So this is the area, this is the area on which the force is acting. What force? The water force is acting. And now, if he goes by physics, he wants more pressure. He cannot tweak the force. So what he has decided, that he has decided to cover half of that opening through his thumb. That's what we do. We cover the pipe, and he has covered. Now the entire area has been reduced to the red shaded portion. Do you understand? So he has reduced the area, resulting which the force has now the pressure has now increased substantially. As a result, the water is now able to, the flow of the water now gushes out till the plants. Very common example that we do. Whenever you reduce the area for the same force or the same flow of water, the pressure buildup will happen. Look at your faucets, look at your shower in your bathroom. If you see, you fully open your tap and then the water is forced to come out through tiny holes. The center ones would be tiny, the surface ones will be even tinier, and thereby they give you what a big jet of water. And then only you enjoy the flow of the water in a shower or in a faucet, right? So the same concept applies here. In this example, what we are trying to see is that if the numerator is kept constant, thus the force is kept constant, if I want to increase my pressure, I need to reduce my area, and vice versa. If I want to reduce my pressure, I have to increase my area. Hope you have understood this. Okay. Once again, a big sorry, and thanks for bearing that. I tried my level best to match the voiceover with the video. Okay. So our next example is all about the delivery persons from Blinkit and Big Basket who comes to our apartment. And you must have seen these people have got bags, and the strap of the bags are very, very wide. One thing to notice for these delivery personnel are that they carry a lot of, what do you call, um, weight with them. Now they can't reduce the things that they are bringing, right? They can't reduce the things. So the force is constant for them, but the pressure has to be reduced to make it comfortable. So can't expect slim or noodle strap bags for them, because if you give noodle strap bags or something, the entire arm is going to get, almost chopped off. It's very difficult. They can't wear in that manner. They can't have a bag with very small or slender straps. So the straps are increased. The area of the straps are broader straps. Broader straps means more area, thereby contributing to less pressure. If you look in your school bags have got straps which are much, much more wider. If you compare it with gift hamper bags, their straps are not that wide, because you don't carry that much load. Your finger will not feel the pressure of a big load. But if the load increases, then what happens? The the pressure has to be reduced, otherwise it is not going to get comfortable for the person carrying. That's why all delivery personals carry bag which have got wider straps. So in school they may ask you a question, why are the straps of school bags wider? The straps of the school bag are wider in shape to cater to more area, so that the pressure gets reduced, because pressure is inversely proportional to area, or we can say if area increases, pressure decreases, right? Our next example is very interesting. Okay, so this is about, I was saying that one of our student who must have, got a sofa, a new sofa has come to their house, and it's the one which has come very new. And let's say once the new sofa comes to your house, you are dancing on this sofa, right? Up and down, you are dancing on this sofa. So what do you expect? That obviously your parents will not take it in the right spirit, right? So if you are dancing up and down on this sofa, then you will obviously get a scolding from your parent. So now let's analyze another thing. Let's say a few days later, okay, God forbidden, the same child catches fever and is not doing well. Parents are also very sad. So they are now, the same parent is saying, why don't you lie down on the sofa and watch the TV and try to eat something? The child is now in fever. Okay. Now try to understand this example. The child's weight has not reduced just because she has a fever, right? So the force exerted by the child in both the cases is same, because it's hardly a day before that she was scolded for standing on the sofa. Now the parents themselves have said that why don't you lie down? So let's look at the force. Now this force of the child when she is standing is almost same. Okay, it doesn't change, which is the weight of her body is same as the force she is exerting on the sofa when she's lying on the sofa. But we as parents are pretty fine. We are also very cautious that our sofa should not get bad. But going by physics, the parents faces are pretty happy, they're not sad. Okay, one of sad, obviously child is not well. What is the reason out here? Okay, if you see in the first case, then the area of contact with the sofa and the child is very small, which is only the area of our feet. So the area is less in the first example. As a result, the pressure exerted on the sofa is much more, thereby having potential chance for the sofa to get damaged, right? Because pressure is force upon area. Now, the force is nothing but the weight of the child, and that weight of the child is constant in both the cases, whether the child is lying down or whether the child is standing. However, the area changes drastically in both the cases. When she is standing, the area is only the area of her feet, whereas when she is sleeping, it is the area right from her head to her entire body till her feet and toes. So, don't we think that the area in the second case is much more? Yes, the area in the second case is much more. Therefore, in the second case, it's a happy scenario. The child is also happily lying on the sofa and taking some food. Parents are also happy that the child is having food and she's taking some rest, and also happy that the sofa is not getting damaged. Why? Because the pressure exerted on that sofa. So I say I've given PA, and two criteria that A is when the child is standing, and capital A when the child is, lying down. And we will find that the pressure exerted when the child is standing is substantially more as compared to the area compared to the pressure when the child is lying down. Therefore, the second case is still acceptable. The first case is not acceptable considering a brand new sofa. So you can now relate these everyday happenings, with your understanding. All comes from that basic one equation: pressure equal to force upon area. And in these examples that we are seeing, what we are doing, we are all varying the area and trying to see how does it impact the pressure, keeping the force constant. Understood? So what does the sofa have? The sofa has got springs below it. The springs become bad if you keep on exerting more pressure on them. Our next example is very stylish, and this example takes us to a date called 14th of February. Now, do you know what's 14th of February? It's Valentine's Day. Okay, it's a Valentine's Day. So 14th February, we have got a gala club night, Valentine's Day ball and dance, where we have an extremely beautiful girl, and her name is Stella. Okay, her name is Stella, and Stella has come to the club, and everyone is dying for a chance to dance with Stella. Mind you, Stella has come to our club wearing stilettos. You know stilettos? They are heels. And also a member who has come to the club on 14th is Jumbo. Jumbo is an elephant who has come to the club. And our friend, one of the students from here, actually has an opportunity. Stella has given him a proposal. You mind if I dance with you? Everyone is dancing for an opportunity to is waiting for an opportunity to dance with Stella. She's extremely beautiful, good looking, but she's wearing stilettos. And our friend has been approached by Stella itself. That's why don't you dance with me? Now our friend has got choice. He can either select Jumbo or he can select Stella. Question arises: whom does he select? Right. Now again apply the concept of pressure. Pressure is force upon area. Now the elephant obviously is much more heavy, right? But the elephant's leg is very big, and it is generally a practice that the leg of the elephant contributes so much to an area that the pressure due to the weight of the elephant is almost taken care of. Whereas if Stella during dancing, and it's known, say, suppose Stella doesn't dance that well, by mistake, if she stamps on your foot with that stiletto's area is very, very less, you will have a potential injury. So, a clever friend of mine said, Stella, if you don't mind, I would be dancing with Jumbo tonight because Jumbo happens to be a far better selection than Stella, considering that both are not that good in dancing salsa. Do you understand? So, elephant is suppose when we talk about elephant, we always know that an elephant is much more bulky. You might be saying that the elephant sir has much more weight, but the elephant's leg has an area which actually takes care. They say that even an elephant's, if you put an egg under an elephant's leg, the egg doesn't crush if the elephant exactly puts its leg on top of that. So there are some pretty good things about elephant. They say in olden days when elephants used to come and attack forts, people used to sprinkle mustard on the floor. Elephant cannot balance itself. Mustard is such a small seed. It's just like as if the elephant is walking on balls. And do you know, and the nice interesting thing about an elephant can't see the bottom. So when an elephant walks, it just puts its legs on the same spot where its forelimbs were. What I mean to say is that if the left right foot of the elephant has say stepped on a zone, the rear right foot will actually, if the left front foot has stepped on a zone, the rear left foot will step on that same zone. The elephant believes that this is a tested path. Now you might say in between, if some thorn or some other insect has come, well, that's a different case. But an elephant estimates his path in that manner. An elephant cannot see what is below it. So this is sometimes a question that they ask. A girl has much more potential chance of damaging your feet wearing a stilettos if she can't dance properly, whereas an elephant will not cause that much of a damage because its leg has much more area. Our next example is that of a tractor. Let's look at a tractor. The tractor runs on what? An agricultural field which is very wet. So there's a potential fear of the vehicle going right inside. So we have to reduce the pressure. So how do you reduce the pressure? More surface area. The surface area, because the weight of the tractor is constant. So with this, have you understood that if force is kept constant, then the way we vary this, how this changes, is this concept clear to you? Right? Now let's give some more example. Now we have to give him a vaccine shot. Right? So a vaccine shot, should we use a sharp needle or should we use a blunt needle? So the question is, you will get a pain, no question arises, because the needle will go inside. Our job should be that the pain should be as less as possible, right? So what is in an injection, what we are doing, there will be, with a humanitarian kind heart, I will be exerting a force. A force is needed to puncture his skin and get the needle inside. If the needle is blunt, then the area is more. So if the area is more, then the skin will be giving me more pressure. So when the skin is giving more pressure, I need more force to penetrate it. It will cause more pain. Like this, it will go inside. And if the needle is very sharp, then in that case, the pressure is much less. It goes inside. So select as sharper needle as it can be. The pain will be much more less. Cutting with a knife, the same thing. Blunt knife as well as another is what? Sharp knife. So the strength comes from where? The strength comes from your muscle. Do we cut by our wrist? Never be in that. We cut by our shoulders. Wrist से नहीं काटते हैं, ताकत यहाँ से आती है. Wrist is only to guide. If you cut with your wrist, you'll get pain. हम यहाँ से काटते हैं. Okay, the strength is coming from the shoulder. So the strength is limited. But if I want to cut really nice, then my knife should be absolutely sharp. Then the area of the knife is, look, how is the blade of the knife? The blade of the knife has some thickness, but as it comes to the cutting edge, it's actually a V. You may not be able to make it out, but it's a V. So the more slim V it is, the less is the area, because the area of the triangle that is forming is less. So I cut much more finer or faster. So he was saying about nail. So look at a nail and a tack. What is this called? This is called a brass tack. A nail is much more blunt, and the surface and the area of the nail is much more as compared to the area of the tack. This is called a tack, a brass tack. So brass tacks are supposed to be pressed inside just by a thumb's force. We need less force? No, we need very less force. Do we need more force? No. But can you put a nail inside here? Take the same nail and take the same board. No, you won't be able to push it with your thumb, because the pressure is much more. So you need more force. So this orientation have we understood? Now let's see the opposite case. Let's go back to a gardener example once again. Right. Now say, what has happened? Now in our next example, this tap is not fully open. Now we'll be playing on the force. The tap is not fully open. Okay. And the gardener has put his fingers as much as he can. Still the water is not reaching the plants. So the gardener tells Sarvesh, pull on Jesse. So he goes and switches it, turns it on. Area is constant now. What is being increased? The force is being increased. So if the force is being increased, automatically what is happening? Pressure is increasing. The pressure will increase. Avigya, not decrease, increase. So we come back to this example, this one. Now we change our actor. Just see here. So one fine day, the same new sofa in Mishka's house, and I have fallen ill. And I come and tell their house that, Mishka, can I lie down on your sofa and see? Will the faces be like this? No. What has happened? And let's say my area, my head to my toe, the back area, is equal to the surface area of her. But our masses are completely different. So once I lie down in this manner, the force goes up
the pressure goes up. ये सोफा क्या हो जाएगा? दबना शुरू हो जाएगा. Do you agree or not? Right? So same case. Let's see more out here. Now, obviously, if the elephant was also wearing a stiletto and Stella also wearing a stiletto, then whom should you select for dancing? Stella. You have to select one. See, you have to select one. Because Stella's pressure will be less. Both will send me to hospital. But in this case, whether I will walk again or not, now whether I will walk again or not, I don't know. It will be drilled, my complete. But this one will.
It'll have even thinner.
No, not thinner. I'm saying the same shoe worn by both. So in that case, here the consequence will be far more. So if you have the tractor wheel, but you have replaced the tractor with the weight of like 2 army tanks, then also it will go नीचे चला जाएगा. That's why army tanks always have a chain drive also. Not only have flat to increase more area. They don't have wheels. They have got a chain drive. And they have got a chain drive also so that you can get multi-terrain movement. Is now force understood? So the questions you might be getting is, why are school bags designed with broader straps? And don't write a lot of Ram Kahani. Answer to the point. School bags are designed with wider straps to contribute to a greater area, thereby reducing the pressure on the shoulder. And in bracket, right, pressure is force upon area. And you can put an arrow. If the area is increased, the pressure comes down. Rollers.
The area, not those.
No, rollers concept is different. Again, the same thing. The roller's surface area is given more because it's supposed to roll a more surface. But obviously, yes, the wider a roller for the same weight, the pressure will be less. It is not called roller. The perfect word in engineering we call for it is called a compactor. That's called a soil compactor. It's supposed to compact your soil.
So as if we force the pressure.
If force provided area is kept constant. आप दोनों को नहीं छेड़ सकते हो. देखो वापस एग्जाम्पल अभिज्ञा यही होता है. बहुत अच्छा. आप इनमें या तो इनको कांस्टेंट रखो और इनको छेड़ो, या फिर इनको कांस्टेंट रखो, इसको छेड़ो. आप दोनों को ही ट्विक करोगे. आई विल गिव यू 4 मैंगोज बट आई विल रिड्यूस द नंबर ऑफ पीपल. देन कैलकुलेशन गोज फॉर अ टॉस. कीप द सेम नंबर ऑफ चिल्ड्रन, increase the number of mangoes, or keep the same number of mangoes, reduce the number of children. Don't play on both. So now again answering your question, force increases, pressure increases provided area is kept constant. Area increases, pressure decreases. Area decreases, pressure increases provided force is kept constant. So let's write one more line before we end for today. So we'll write like this: pressure is, we say pressure is directly proportional, and this you will understand when you do proportion chapter, directly proportional to force. But don't forget to write the condition, provided area is kept constant. Have you understood? Force is directly, pressure is directly proportional to force, provided area is kept constant. Let's look at our next line. We will write pressure is inversely proportional to area. And here what is the condition? Provided force is kept constant. How difficult it is to add voiceover to a video. First, you have to see the video and then recall what I spoke there. And that to match it. Not time consuming. You don't know what is the next scene that is going to come. So I have to use 2 monitors. In one monitor, I have to play the scene a little bit ahead so that it keeps on coming in my mind. And then the first time I'll do that. Have you understood? Directly proportional मतलब कैसा है? देखो, maths में हम सीखेंगे. Directly proportional. If the more hotter the days of summer, what about the ice cream sales? The more the sale will happen. अगर एक क्वांटिटी को बढ़ाने से दूसरा क्वांटिटी बढ़ता है तो डायरेक्टली प्रोपोर्शनल। समझ में आया? Have you understood? The more the number of people I employ to clean this house, the time taken will be less. अगर किसी क्वांटिटी को बढ़ाने से दूसरा क्वांटिटी घटता है, इसे हम क्या कहते हैं? इनवर्सली प्रोपोर्शनल। इनवर्सली प्रोपोर्शनल, है ना? जितने ज्यादा लोग, जितना स्पीड बढ़ाएंगे उतना टाइम कम लगेगा, जितना डिस्टेंस बढ़ाएंगे उतना पेट्रोल ज्यादा लगेगा। दैट इज कॉल्ड डायरेक्टली प्रोपोर्शनल। So our Rangarang Karikram for today comes to an halt. And children, let's make each other happy. End of the day, the whole fiasco of today happened. 2 people being sent to prison, recording getting stopped. What is the root cause analysis if you do? Like a management consultant? Bad mood. And who created that? So, you understand how cascading it happens? Not you. You do ethic. Yeah. And remember one thing when you are studying with me. Submission is not just because you have completed it. Submission is when you feel it is worth submitting. Give your best shot. माँ भी जब बच्चे को खाना खिलाता है ना, यहाँ से गिरते रहता है ना, ऐसे फिर उठा देता है. Because the mother wants the face also to look good by the time the bacha is eating. And I believe in perfection. It's not that I take time. मैं आपको कोई भी एरा गैरा डायग्राम ड्रॉ कर सकता था, मैं ऐसे क्यों ड्रॉ करता हूँ? देख के भी ऐसा लगे ना कि हाँ बच्चे पढ़ने आते हैं, सर्कस करने नहीं आते हैं. जब एक ट्री भी बनाएंगे ना तो ट्री भी ट्री जैसा लगना चाहिए. हाँ, now if you're an enemy with me and say no sir I don't think it is a tree, it's a mushroom, वो अलग बात है, वो तो मेरे दुश्मन हो, इसे तो मुझे समझ में नहीं आ रहा. Shall darling, and I have forgotten everything of today, and I want you not to forget. Always remember, it is not scolding or it is not chasing. You all are not cow and goat. ऐसे ले जाएंगे. You're not cow and cattle नहीं हो. Class दिखाओ. इतना अच्छा अच्छा pencil box and instrument box and that is the output. Sir, we make roti with compass. What is the shape? Sir, like Australia's map.